one might ask, what would happen if I have a loop carrying a current I, like in this here? Now, if we have a loop carrying a current I, it's going to result in a magnetic field. The direction of the magnetic field is determined by the right-hand rule, like we have used for a long straight wire. We wrap our hand around the loop, and our thumb is going to be in the direction of the current. Now, as you notice in this particular picture, when we have the current going in the counterclockwise direction, when we wrap our hands, our fingers, our nails, as they go through the plane of the loop, are coming out. So the magnetic field inside the loop is going to be pointing towards us. Outside the loop, our fingers, our nails are going into the screen, so the magnetic field outside the loop is going to point into the screen. This is another representation of the same thing. So the magnetic field inside is going to be pointing up for a current. I'm not sure if you notice it. The arrow is pointing this way for a current pointing in that direction, so going in the counterclockwise direction. Now the magnetic field outside is going to point this way. Now, thinking about this in terms of a magnet, the magnetic field lines are coming out, so this looks like a north pole, and this looks like a south pole. Okay, consider this simulation. Okay, you notice here the magnetic field inside is pointing in one direction, but around the wire it's going around in a circular fashion. So outside it's pointing in the opposite direction than inside the loop. Okay, we can move this up and down. You see now when we are out, it's all in the same direction, but the minute we are inside the loop, it's different directions. And we can find the we can find the direction of the current, for example, here by using the right-hand rule. Our fingers should be pointing the same direction as the arrows. The tips essentially is where our nails are. So if we wrap the right hand, that tells me that the current here is going in this direction. Now, what if I have many loops in what we call a solenoid, something that looks like this? We are going to use the same rule for the direction of the magnetic field. As you notice, we have here a south pole and a north pole, like a bar magnet. Now, if we have the current going up like that, using the right-hand rule, the thumb is going to be in this direction. We wrap our hand around the wire, so our nails are going into the loop in this direction, and that's why the direction of our magnetic field is that way. The expression for the magnetic field is mu times Ni. Now, if I don't have anything inside the solenoid, if it is an air core solenoid, instead of mu, we use mu0. Otherwise, we use mu that corresponds to the material that we have in. Now, the other thing to pay attention to, N is not the number of loops, it is the number of loops per unit length. Okay, that's important. So let's look at this in terms of this simulation. So what about if I have a number of loops? And this is what we have. Now, you notice now here the arrows are actually representing the direction of flow of electrons, not the current. Now, if the arrow is moving this way, now our thumb should be in the opposite direction, and that's the way you see the right-hand rule. Now, the red arrow is pointing to the direction of current. Now, if we follow the red arrow, let's see if we can follow it. Now, for the red arrow, okay, it is going down. So if we wrap our hand in here, the direction should be towards the left. Our fingers are going inside the loop, in the middle of the loop, and away from the loop, outside the loop. Now another thing I would like to show you here, we have two loops that are far away from each other. Each one of them results in a magnetic field like what we see from one loop. Now as we approach them, you notice here that the field from this one, from the left one on here, is pointing down, while the field from this one in this direction is pointing up. However, in the middle, they are in the same direction. In the outside, they are in the same direction. So what this means, as we get them close to each other, in here, the fields are going to cancel each other out, and all what's going to matter is the field inside and the field all the way outside. Okay? And that's what results in a solenoid, and that's what gives it this particular property. Now, again, this is our equation. If I have an air core, it's mu0. N is the number of loops per unit length. So if I have a total number of loops and I measure the length of the solenoid, I can get small n. And we can use the right-hand rule to find the direction of the magnetic field. Now, if I have a core inside that's not air, I need to have mu instead of mu0. But pay attention to the fact that it acts like a magnet, having a north and a south pole that we can determine with the right-hand rule. Okay. This is a picture of a magnet, a solenoid with a core inside. So in that case, we use mu instead of mu0. Here it's mu0. Okay, and one last thing. This is a picture of the record-breaking 35 Tesla magnet at Florida State University.